We're going to go on to look at cardiac muscle and electrical activity. And I've gone ahead and opened up all the pictures I want to work from. First off, this is a picture of cardiac, would help to turn off the freeze thing, wouldn't it? This is a picture of the structure of cardiac muscle tissue. You might have looked at it in A&P 1. I personally tend to reserve that for this point in A&P 2 when we look at it a little bit more closely. The little micrograph off to the side there highlights an important feature that we see in cardiac muscle tissue on a microscope, which are these features called intercalated discs. And they're kind of faint. They really are hard to see, but there are these lines that are going across the fibers, like we see these two labeled. Here's another one right here, which is not labeled, so it's not covered up by another black line. But what those are where individual cells come together. They stain darkly because where the cell membrane from one cell comes together with the cell membrane from another cell, they are held together by some proteins. And those proteins, the adhesion proteins, pick up a good bit of stain, and so we can see that in the tissue when it's stained well. Now, what we don't see in that tissue, and it's actually not commonly seen in most cardiac muscle tissue in the microscope, is the fact that it's striated muscle. When you learned about skeletal muscle, you learned that was striated. And the striations came again from the staining pattern of the proteins in the tissue. The dark bands were where we saw myosin. And the myosin basically lined up in all of the myofibrils, so you can see it all in one stripe across the tissue. And then where there wasn't myosin, we saw the light bands, which alternated back and forth. That's why it's called striated tissue. Cardiac muscle tissue is striated also, but the myofibrils aren't quite as significant portion of the cell, so they don't usually stain quite as dramatically as we'd see in skeletal muscle. But the two types of muscle tissue work on the same principle, which is what you learned last semester about sliding filaments and myosin and actin and all that kind of stuff. So that doesn't change. What is different is how the two types of tissue have to solve essentially the same problem, which is how to translate contraction at that organelle level, the sarcomere contraction stuff, how to translate that up to the entire organ contracting. Skeletal muscle is fairly straightforward because what it's doing is pretty simple, straightforward physics. It's just pulling two sides across a lever, across a hinge or a lever to create movement. And so it's pulling point A and point B closer together, the origin and the insertion of a muscle closer together. And so the contraction is completely linear. And what happens is the cells that are part of the developing muscle tissue all merge together into one big cell. So the myoblasts seen in developing tissue mature into skeletal muscle tissue by merging together, making one long muscle fiber that goes all the way from the origin to the insertion of the muscle. And so when that muscle contracts, the whole length of the muscle is contracting at once. Cardiac muscle has to solve a similar problem, how to get something that's happening at the cellular level to translate up to something happening at the organ level. And the way that this cardiac muscle does that is different because the heart is different from skeletal muscle. And what's different is basically the shape. Skeletal muscle is very linear. It's always pulling an insertion towards an origin, point A into point B, coming together. For cardiac muscle, it's different because the heart is a three-dimensional structure. And so the cells need to be individual because they build a three-dimensional structure. You can't have one big cell wrapping all the way around and making the three-dimensional shape of the heart. And so the depiction of the muscle cells that we see here, where they have a good bit of branching and that sort of thing, that lends to the three-dimensional structure of the tissue and therefore the three-dimensional structure of the heart. But they still have to all contract as one. So what's going on at the intercalated disc is essentially the cardiac muscle's solution to the similar problem. So we can see the intercalated discs represented by this squiggly line here and the dissected apart cell or exposed cell. And on the outside, we can see it here. Over here, we have a cell that ends. And it looks kind of like, egg crate foam rubber or Velcro or something like that. So you can imagine something that's sort of the same shape as this fitting in and they interlock together. And that's what's happening at the intercalated disc as we see it in these other spots in the drawing. Down here where they have one exposed, they've drawn a box around it because down here is a little higher power representation of that. I can't quite get all of this on the screen, so I'll move it around a little bit when I need to. And so the sort of Velcro or egg crate shape that I described where two cells interlock together is represented in this kind of back and forth curvy part. And along the length of this, we see some connection points represented in desmosomes, which are just cell adhesion complexes. If you don't remember about desmosomes, they're covered in the tissue chapter, talking about epithelial tissue. Desmosomes are one of the things that help to hold those cells together. So if you want a reminder of what desmosomes are, go back to that chapter, and in the epithelial section, it describes the different things that act as connection points. Now, here we see the sarcomere pattern of representing a myofibril in one cell and the same thing in the next cell. They're kind of lined up together so that the contraction is sort of happening along the length of those cells. And then this sort of fuzzy stuff we see here represents what would be kind of a connection point between those two. Now, if you go back into the tissue chapter and you look at where desmosomes are, it's going to describe other types of connection points. What's going on here isn't one of those types of connection points, but it's similar to them. The cytoskeletal proteins in epithelial cells integrate with the cell membrane, and there's attachment from one cell to the other, and the cytoskeleton ends up being sort of this continuous network throughout the entire epithelium. That's the same thing going on here. The proteins in the sarcomere structure, the myosin and actin and that kind of stuff, those are cytoskeleton proteins. It's just in muscle tissue, they're sort of repurposed for the contractile properties that we studied in AP1. But because they are really cytoskeletal, they are involved in some of the connection points like we see here. Okay. So here's another desmosome, and here's another place where we have a connection point across where the myofibril is. And then this takes a turn, and the intercalated disc area runs for a little while along the length of the two fibers side by side. And the connection points that we see here are different. These are what are called gap junctions. And again, back in the tissue chapter where it's describing desmosomes, they described gap junctions also. What they are is ion channels, but they're ion channels as an attachment protein. Now, they're not primarily there for attachment, but they do attach from one cell to the next. I have two pieces of tarp here, which I've cut off. I've cut out of the tarp where the little grommets are. So if you have, plastic tarp like this and you tie it down, this is where you tie the tarp down. I'm using this to represent the cell membranes of two adjacent cardiac muscle cells. So where this grommet is, that would sort of be where this half of a gap junction is. And where this grommet is where that half is. So they're each sort of channels through their respective cell membranes. But they line up and they actually attach to each other at the gap junction. And so we see two channels acting as one that goes all the way through both cells. And what that allows for is ions in this cell will pass directly through into this cell, okay, which means that the cells are electrically coupled. Okay, remember, the movement of ions is what causes depolarization, repolarization, all that kind of stuff. And so if the ions in one cell move freely into the adjacent cell, they act as one electrically. They're electrically coupled. What that means is if this cell depolarizes, the sodium that's rushing in to depolarize that cell is going to continue through the gap junctions and depolarize its neighboring cell, which is then also going to, it's going to do the same thing electrically. Let me go back up to this picture here for a second, where we can see this a little bit bigger. So when this cell depolarizes, the sodium that's depolarizing is going to rush into the adjacent cell here, cause it to depolarize, and into this cell here and cause it to depolarize. And then this cell is going to connect to its neighbor, which isn't drawn in here, and cause it to depolarize. This cell is going to depolarize its neighbor here, which will then go on to depolarize its neighbor through this fiber and go on and depolarize the neighbor this way, and there must be another neighbor out that way. So as one cell depolarizes, since the sodium that's doing the depolarization can easily move through those gap junctions, all of the neighboring cells are going to depolarize and just sort of continues on through all of those cells. They act electrically as one structure, and that helps to tie everything together so that with that spreading depolarization, the cells are going to contract, and you're going to get coordinated contraction across the entire heart, which is how the heart or cardiac muscle solves the same kind of problem, how the whole organ behaves as one based on the cells that make up its tissue. Now, the reason that's important is because in the heart, there are dedicated muscle cells, and these are cardiac muscle cells, which conduct the electrical signals throughout the heart. We call it the cardiac conduction system, or the cardiac conduction pathway. There's essentially 5 different spots along the pathway. Okay. It starts with a node, a little cluster of cells right here in the wall of the superior region of the right ventricle, fairly close to where the superior vena cava drains in there. This node is called the sinoatrial node, or the SA node. We'll just refer to it as the SA node for the most part. But sinoatrial refers to 2 different ways of referring to that chamber. That's the right atrium, obviously, so that's where the atrial part of the word comes from. But we can also think of this as a sinus, which is where the word sino, or the root sino, comes from. A sinus in the circulatory system is really just an enlargement of blood vessels. So where the vena cava comes into the right atrium is really just an enlarged chamber on the vena cava. So we can kind of call it a sinus there. So that's where sinoatrial node comes from. The sinoatrial node is connected to all of its neighboring cells, and that's going to spread through all of the right and left atria. In the wall of the right atrium, at the junction between the atrium and the ventricle on the right side, is the atrioventricular node, or AV node. Same word as the AV valve, because in both situations we're talking about something at the junction between an atrium and a ventricle. That's the only relationship they have. They have the same word describing the same position, but the valve here and the node here are otherwise not related to each other. So the SA node will send an electrical signal that'll spread throughout both atria, which will include reaching the AV node. Now, in this picture, in a lot of sources, they'll draw in these yellow lines here, which are internodal pathways. They're not crucial to understanding what's going on here because these white lines represent the spreading depolarization throughout the rest of the atrium. And there's going to be depolarization that spreads and reaches the AV node no matter what. But there are technically some dedicated pathways to that. From the AV node, the pathway continues on towards the ventricular septum, the wall between the right and the left sides. The bundle of fibers going from the AV node down to the septum is called the atrioventricular bundle, or the AV bundle. The sort of old-fashioned name for that is the bundle of His. Some dead white guy whose last name was His discovered it, and so it was named after him. But that's very rarely used. That's what we call a dead white guy name. And we'll refer to it as the AV bundle. Okay. The AV bundle then, once it reaches the interventricular septum, will branch into a right and left bundle branch. So we're looking at the right and left bundle branches that continue on down the length of the septum to the apex of the heart, or the pointy corner of the heart. The left bundle branch then goes up into the left ventricular wall, and the right bundle branch goes into the right ventricular wall. Now, in pictures like this, it always looks very two-dimensional. It looks like one branch goes up this side and the other branch goes up this side. But really, it's a three-dimensional projection, so it kind of goes all through the entire ventricular wall. Okay. Branches off of the right and left bundle branches are called Purkinje fibers, which then connect to the ventricular myocardial cells and spread the signal through the rest of the ventricles. Now, I just pointed out the bundle of His being a dead white guy name. Purkinje is also a dead white guy name, but I've just always kind of dug that name, Purkinje. That's a real horrible pronunciation of his real name. It's like Purkinje or something like that. But everybody pronounces it Purkinje. He was a very prolific anatomist, dead white guy anatomist. So there are a lot of things named after him. This one kind of sticks, and a lot of the things that he names kind of stick, largely because there's not a good functional name for a lot of those things. These are fibers that conduct the signal from the conduction pathway to the rest of the myocardium and the ventricle. I've seen some sources try to call them conduction fibers, which is really not good because there's nothing special about them versus the rest of the entire conduction system. So all of the things that are colored yellow here are conduction fibers to some degree. So to call the Purkinje fibers conduction fibers is really not a great name choice. So I tend to stick with the name Purkinje there. And most sources do. It's very rare that you see them call them anything else. The bundle of His is pretty much always called the AV bundle nowadays, but Purkinje fibers are usually still called Purkinje fibers. Now, everything that's yellow here, all of the pathway that I just described, this conduction pathway, these are myocardial cells. These are cardiac muscle tissue cells. They're just specialized for conducting electrical signals rather than contraction. Remember, muscle cells have their own action potentials, and they can conduct electricity. It's just we've usually associated that with causing the release of calcium and contraction. Here, contraction really isn't the point of what these are doing. These are specialized for conduction of electrical signals, and it spreads from the SA node through all of the atria, or from the bundle branches and Purkinje fibers through all of the ventricles. And that's how the signal spreads throughout it. Everything here is a cardiac muscle cell. Some are just specialized for specialized for conduction, and the majority are contractile fibers. But they're all interconnected by the gap junctions at the intercalated discs so that When one depolarizes, it eventually spreads throughout the entire heart. So let's talk a little bit about that one that depolarizes. The SA node is essentially the starting point for this. And it's going to depolarize, generate an action potential, which will spread through this whole system and cause everything in the heart to depolarize and eventually contract. And then it's going to do it again a very short while later. Okay? It's referred to as the pacemaker of the heart because it sets the heart rate, the pace. Now, usually when we hear the term pacemaker, we think of artificial pacemakers, but really those are things that help fix problems when the SA node isn't doing its job correctly. Now, the way that the SA node works like this has to do with the fact that it's made up of cells that are autorhythmic. They generate their own action potentials. And this is a representation of what those action potentials are kind of like. Now, I say kind of like because I don't entirely, well, I'm not a cardiac physiologist. I'm really more accustomed to neurophysiology. So the numbers here don't quite jive with what I expect to happen in excitable cells. But again, that might just be because I'm not that familiar with the heart. These are the numbers that we tend to see. And they're probably different from what you learned in A&P1, where we had negative 70 resting potential, threshold at negative 55, a peak at positive 30, hyperpolarization to like negative 80, all that sort of thing. Those numbers don't quite correspond here. And the fact that they don't isn't terribly important. The process of what's going on here is very similar with one really big difference. So threshold is at a different value, but still once the membrane hits threshold, voltage-gated sodium channels open and a lot of sodium rushes in, depolarizing the cells. Okay. Now it says calcium here because in the heart, actually calcium and sodium can both play a role here, but there can be sodium rushing in there, and other sources will say that. When it hits its peak, the depolarization ends and potassium leaves the cells, causing repolarization. Instead of getting down to a resting membrane potential and just sits there doing nothing for a while, these cells actually start to depolarize again through what's called the pre-potential, and that is definitely dependent on sodium. Okay. So the rapid depolarization, here they include calcium. I'm not entirely sure that's perfectly correct. Again, I'm not really a cardiac physiologist, but there really isn't a voltage-gated calcium channel, I think, that really works that way. But that's beside the point. The pre-potential is important. There are sodium channels that are kind of always open to some degree, and they allow some sodium leak in these cells. So even after the action potential has gotten way back down to negative 60, according to this figure, the membrane potential is going to slowly creep up to threshold again. It'll never sit at resting potential doing nothing. These cells are always doing something. And then when they hit threshold again, we get the rapid depolarization, the repolarization, and then we have pre-potential depolarization again. Okay. This is always going on over and over again. So these cells automatically have generate an action potential, and then they slowly get up to threshold to cause another action potential, and then they slowly get up to threshold to cause another action potential, and then slowly get up to threshold to cause another action potential. These cells are always doing this. Now, in this graph, the time from the first action potential to the second action potential here is at 0.8 seconds or 800 milliseconds. When the cells are depolarizing and firing off action potentials at that rate, they're going to be firing off action potentials about 75 times per minute. Okay? So this represents the resting heart rate. Now, it's kind of unfortunate they do this, but pretty much every book does this, so I'm not going to complain too much. The reason why it's kind of unfortunate they do this is because this is not exactly what the SA node is going to do all on its own. By itself, the SA node will depolarize at a rate of about 100 times per minute. So without any autonomic input to the heart will automatically beat at 100 beats per minute, because these autorhythmic cells in the SA node. The parasympathetic system hyperpolarizes those cells so that the prepotential is slower getting up to threshold. And that's going to slow things down enough to get the heart rate to drop from 100 to 75 beats per minute. The sympathetic system, if it's going to have an effect, will actually speed up depolarization, and then the heart rate will speed up past 100 beats per minute. But since we're usually thinking about resting heart rate, and we're going to see that 0.8 seconds all the time talking about a heartbeat, they put it in here just so it doesn't really confuse you. But do understand that this is resting heart rate, which is really modulated by parasympathetic input. What's really happening at the SA node is, without any input, is that it'll beat faster. And in fact, the heart will beat on its own completely. Okay. You can take the heart out of the body, and as long as you provide it with nutrients, it'll keep beating, which until recently was just kind of an interesting thing to say. And in fact, a lot of early understanding of cardiac physiology and neurophysiology, and in fact, the discovery of acetylcholine was based on somebody doing that. Okay, a German physiologist removed the heart from a frog and kept it alive in a nutrient bath, and was able to adjust its activity based on adding secretions from the vagus nerve, which is acetylcholine. And that's how acetylcholine was discovered, by removing a heart from the body, again in a frog. Nowadays, actually, it's kind of interesting to talk about this, because for heart transplants, recently somebody's invented a way to keep the heart preserved better from when it's removed from the donor to when it's transplanted to the recipient. When people talk about organ donations, aside from the urban myths of people waking up in ice baths or something like that without a kidney, really organ donation, you usually think of red igloo cooler. Okay, you've probably seen something like this, somebody rushing around with a cooler that has some organ on ice in it. Okay. The point there is, by cooling down the organ, whether it's a heart or whatever, you can preserve its anatomy and therefore physiology long enough before it can be implanted back into a body, and it will be able to survive after that. Recently, something's been invented, and I wish I had a link to it. I've never found a very reliable link showing the video of this. But somebody's invented, I think they call it the heart box. And a heart's removed from the donor, and it's put in this box. It's hooked up to some nutrient fluids, and it sits there and it beats just like it would be in the body. And it's closed in this box, and it's transported. It doesn't have to be put on ice, and it can survive longer than it would in that red igloo cooler as it's being transported. Cooling down the tissue actually potentially damages it some, because low temperatures can mess up cell membranes, that sort of thing. So it's a little bit better to do it this way, and the timing required between donation and transplantation is extended. Look online if you want to. There's a video I've seen somewhere, and again, I've not been able to locate a reliable link for it. Like, I find it in some news site talking about this, then the news site takes it down or something like that. So I don't have a permanent link to it. But search for, I think if you search for heart box or something like that, you'll probably find a video showing it. But that's just to say that the heart actually beats on its own, and it'll beat at about 100 beats per minute. And what we see here, this 0.8 seconds represents the heartbeat being slowed down by the parasympathetic input. Now, actually, if you're going through the book, this figure comes after this figure here, because what I wanted to do is talk about that autorhythmic nature of the SA node a little bit before we look at the process of what's happening for the conduction pathway. So here we have basically 6 pictures running through the process of how the conduction system works and how that corresponds to the contraction of the myocardium. So what happens first, so the start point, the SA node is going to generate an action potential, okay? Which they don't really have anything in this particular part of the picture to suggest that's happening, but there's a little bit of a halo of purple around the SA node here, and the lines spreading out from it represent the fact that the signal is going to spread through the adjoining tissue. Now notice the wall of the atria at this stage compared to the wall of the atria here as the purple spread throughout all the atria. Okay? So now the depolarization is spread through the atria, and that's going to cause contraction. So the fact that the atrial wall on either side looks like it's kind of collapsing in represents the contraction of the atria, which is going to help to pump blood from the atrium down into the ventricle. Okay. As that depolarization spreads all the way through the atria, it's going to reach the AV node, which we see right here. And so now we're no longer really paying attention to the atria, but rather to the AV node, so it's turned purple. It's going to conduct the signal along the AV bundle and into the interventricular septum, where it branches right and left. And that's going to spread down to the apex, which is then going to spread up on the right and left sides, as we see here. And because of the connections through the Purkinje fibers, as we get to the next one, we see depolarization spreading through the ventricles. Now, I have a feeling these two pictures here, 5 and 6, look kind of identical. I think what was meant to be shown is the purple in 5 should have only spread maybe halfway, and then 6 is spreading all the way through. That's what that should show. The point there is, since the bundle branches go down to the apex and then curve up into the wall on either side, depolarization starts at the apex and then spreads up from that point towards the top of the ventricles, which is where the semilunar valves are located. So as the ventricles contract, they pump the blood up towards the valves where they're going to eject the blood. Sort of like you would squeeze toothpaste from the bottom of the tube towards the top where the opening is. Same thing's going to happen here. So I think even though these two pictures are technically, exactly the same, I think the purple shading is supposed to only go about halfway up here and then go all the way up here, just to represent the spreading of the depolarization across the ventricles from the apex towards the base of the heart, which is where the valves are located. So again, this is just a circle, a circuit, cycle, that's what I'm looking for, cycle, representing how this happens within one heartbeat. And then it starts all over again and goes through again. And this is going to happen every however many times a minute that the heart rate represents. So 75 times a minute for resting heart rate, 100 times a minute if the SA node's working on its own, maybe 150 times a minute if you're in the middle of serious exercise or something like that. I just keep going around and around. Okay. Now, I want to talk a little bit about what's happening in the actual myocardium, in the cells that aren't really part of the conduction pathway, but the cells that are getting the signal from the conduction pathway. So this picture, which is actually only part of a bigger picture, and I'll show you the rest of it as I discuss it and kind of unveil the different things. This is looking at skeletal muscle activity. So this is basically what you would have learned in A&P 1. The numbers here, again, aren't exactly what you might have learned in A&P 1, but the concept is just fine. So starting at a very negative value, which would be resting membrane potential, maybe, the action potential shoots up. Again, that's dependent on sodium entering the cell, and it hits a peak, and then it repolarizes because potassium is leaving the cell, and then it hits resting potential.
that single very brief action potential will lead to a particular shape of a contraction curve, what we would call the muscle twitch. Okay. Now, there are different types of skeletal muscle fibers. There are slow fibers, there are fast fibers, there are intermediate fibers. This particular curve here would probably represent an intermediate fiber. So it's about 50 to 70 milliseconds worth of contraction time based on a single action potential. Some fibers contract slower. They might be 100, 150 milliseconds worth of contraction. And those are the slow fibers. And then fast fibers are going to have very rapid contraction curves, which would probably look pretty much exactly like the action potential in this drawing here. That'd be like a fast fiber, like in your extraocular muscles or something like that. So this is what you learned about last semester. It's different in cardiac muscle tissue. Okay. So this is what the action potential looks like for your average cardiac muscle cell. Okay. The action potentials you're looking at before were for the SA node cells, or for the autorhythmic cells in the conduction pathway. Here we got something very different. And partly what we're going to see here makes me think that that calcium thing that I pointed out that I don't quite believe, I think this is going to kind of show why that calcium is probably not entirely true. So we go from some very negative resting membrane potential, and we depolarize, and we get a very rapid rise in membrane potential, which is sodium dependent. And we have on the backside a repolarization, which is potassium dependent. So those things are basically the same. Okay. What's different is what's in between. So from the peak to the actual falling phase, the action potential kind of sits at a rather depolarized value. And that's actually due to calcium, which we'll see in a second. But by causing this rapid depolarization that's maintained for a while before it falls off, that leads to a contraction curve that's much broader. There's about a 300 millisecond time span for the contraction here in the cardiac muscle cell. Now, I said this is your average cardiac muscle cell. By that, I mean a ventricular muscle cell. The ventricular walls are much thicker than the atrial wall. So just by number, the vast majority of myocardial cells are in the ventricles. And they have a contraction curve like this, of almost 300 milliseconds long. If we're looking at an atrial wall, what we see is still kind of similar, but it's going to happen over the course of about 100 milliseconds. So it just has a shorter contraction curve, shorter action potential, and therefore a shorter contraction curve. But we usually pay more attention to what's happening in the ventricles anyways, so that's fine here. Now, here's where we start to see the ions that are at play here. Okay, so to begin with, voltage-gated ion channels open at threshold, and we have rapid depolarization. That's due to sodium, just like we learned last semester. Then there are calcium channels that open, and they keep the membrane depolarized for a while in what we call the plateau, suggesting that's kind of a flat depolarization. And then eventually those calcium channels close, and we go into the potassium-dependent repolarization. Okay, so the rapid depolarization and the repolarization in skeletal muscles, neurons, and cardiac muscle cells, like we're seeing here, pretty much the same thing. Sodium rushes out, potassium rushes in. The difference is, in between those, in cardiac muscle cells, we have this plateau which is maintained because calcium is entering into the cell. Okay, calcium is a positive ion, so as it enters into the cell, it's going to keep it depolarized. Now, when you learned about skeletal muscle cells last semester, what did calcium do for those cells? What was the point of calcium in those cells?
Start the action potential.
No, sodium starts the action potential. Calcium's actually not involved in the calcium. Calcium's not involved in the action potential. Calcium's involved in something later on. Where do we find calcium in the muscle cells? Skeletal muscle cells.
Mitochondria.
Sorry?
Mitochondria.
No? What's the storage compartment? It's one of those things that has a funny name for muscle cells, but it's really the same thing that we find in other cells.
Sarco something.
Yeah, sarco something. Sarco something contains calcium. What is it? The sarcoplasmic reticulum, right? Which is essentially the smooth ER. Okay? When calcium is released from the sarcoplasmic reticulum, what does it do? So someday somebody's going to be listening to this on YouTube and they're going to be sitting here going, my, why is it so quiet? And it's because you guys are really trying to think hard of what you learned in A&P1. What does calcium do in skeletal muscle cells? It's released from the sarcoplasmic reticulum into the cytoplasm. What does it do there? What are muscle cells about? What's their job?
Contract.
They contract. Why do they contract?
Create movement.
Okay, so yeah, why is kind of a vague term, I suppose. They contract to create movement, but why does contraction take place in that cell? What's happening during contraction?
Channels opened. Are they stimulated by the neurons?
We're past that. I've already told you that calcium is being released from the sarcoplasmic reticulum. So what's causing contraction? What is contraction?
Sliding filament thing.
Yeah, it's a sliding filament thing. What's sliding? What are filaments? There's the actin filaments and, I said this earlier today, myosin, right. But that doesn't always happen. It's when the calcium's present that it happens. What does calcium do to make it possible for myosin and actin to interact for sliding filaments? What's in the way? Yeah, tropomyosin, which moves because calcium binds to give you a hint, sounds a lot like tropomyosin. Now, the part that's not similar is the myosin part. Troponin, right. Calcium binds to troponin, that moves tropomyosin out of the way. Myosin heads can bind to actin, and the sliding filament thing happens. Okay. That was fun. So there are sarcoplasmic reticula, I suppose that's the way to say it, in cardiac muscle cells, but they're not a really big deal. More importantly, the calcium is coming in during this plateau. Okay. So as calcium's entering into the cell, it's going to be, so here's the plateau, calcium's entering in, and that's what's allowing for contraction. In skeletal muscles, the action potential eventually opens calcium channels and calcium rushes in and causes contraction. But the calcium is actually part of the action potential thanks to the plateau. And so contraction is really tied right to the action potential in cardiac muscle cells. Okay. And the contraction takes longer. And again, this is really for the ventricular cells when this time course that we're looking at here. Atrial cells do the same sort of thing, but they do it in about 100 milliseconds instead of 300. So, now, let me remind where we are. Okay. So this is sort of describing what's happening electrically in the heart and how we're getting to contraction. If we want to measure what's happening here, we have a very powerful tool called the electrocardiogram to do that. So this picture here is showing where we would place electrodes for an electrocardiogram. Okay. They don't have to exactly be in these spots necessarily, but there's going to be one, associated with the right arm, which is often at the wrist, but just as easily could be at the shoulder. Okay. And then there's one on the left arm, might be the wrist, could just as easily be at the shoulder. And then there are two at the ankles, which the ankles are more often used than the wrists in modern preparations, but it's entirely possible that those would be at the hips, and they would essentially do the same thing. So there's right arm, right leg, left leg. And then there are 6 electrodes that are placed across the chest. The first one is just to the right side of the sternum, and then second, third, fourth, fifth. The 6th one is really kind of around on the side of the thoracic cavity over here. So we have 10 electrodes. These electrodes make it possible to measure the electrical activity that's generated by the heart because somebody discovered a very reliable way to do this. An important part of that is that the right ankle electrode is a grounding electrode. So that basically tells the machine what background electrical activity is going on, and we can subtract that out versus what's recorded at the other electrodes, and we can isolate the electrical activity for the heart specifically. Okay. And as we do that, the electrical activity as it changes in the heart is represented in the EKG trace like we see here. Now at the top on the graph paper representation, we have 4 heartbeats represented. And then in the box, they're showing us 2 specific heartbeats worth of time here. And it's also labeling the different events that we see recorded. Now what's happening here, there's a 0 point. There's a pen that's sitting there. The pen either goes up or down depending on electrical changes recorded based on activity in the heart. It's just recording changes. So when we see this bump right here, that's just showing us that something changed. And then when we're at this flat line 0 part here, that's just telling us that nothing's changing. This isn't the electrical charges that we're measuring in the heart. It's not like we're seeing action potentials here, but rather events that are at the beginning and end of action potentials. Okay. So for some reason, I can't remember anymore exactly why it is, the first event is called the P wave. That P stands for something. And that's followed by a Q wave, an R wave, and an S wave that always come very close together. Collectively, those 3 waves are referred to as the QRS complex, which we see down here. And sometimes we don't see all 3 waves, but the events happening right there just collectively called the QRS complex. And then we have finally the last event, which is a T wave. And then there's a flat line for a while, and then we see the P wave, QRS complex, and T wave of the next heartbeat. And actually, if we go through here, we have P, QRS, T, P, QRS, T, P, QRS, T, P, QRS, T, et cetera, et cetera. It just continues on and on like that. Now, what these things represent, again, are electrical changes in the heart. The P wave represents when the SA node depolarizes and that depolarization spreads through the atrial walls. That depolarization lasts for about 100 milliseconds, but the P wave is just the beginning of that. The end of that, about 100 milliseconds later, is somewhere here in the QRS complex. But we don't really see the end of that depolarization or the repolarization of the atria because there's a much more significant electrical event that happens right on top of it. The QRS complex represents the depolarization of the ventricles. And they stay depolarized for about 300 milliseconds. I think technically it's like 270, but they stay depolarized for longer than the atria. But while they're depolarized, there's no changing events. So the pen goes back down to 0. And then the T wave is when we see repolarization. So QRS to T represents the depolarization of the ventricles. P to something that's technically hidden behind the QRS complex is depolarization or repolarization of the atria. The fact that we don't see the repolarization of the atria actually gets at the fact that this whole system's set up to kind of make all of this happen exactly at the right time for this to be as efficient as possible. In the conduction pathway from the AV node to the AV bundle and the bundle branches, the conduction's actually slowed down a little bit to separate the atrial contraction or the atrial depolarization from the ventricular depolarization. It's not slowed down because the ions are told to wait for a little while, but rather the fibers in the AV node and AV bundle are narrower. And just this is true of an axon or a muscle fiber. A thinner muscle fiber will conduct electricity slower than a thicker fiber. And so the conduction pathway slows down so that the atrium can do its thing before the ventricle does its thing, just by having narrow fibers there. Now, there's reference to PR intervals and QT intervals and PR segments and ST segments, that kind of thing. Don't worry about those. I'm not terribly hung up on what those are about. Essentially, the PR interval is what's happening in the atrium, and the QT interval is what's happening in the ventricles. But I'm not going to ask you about those intervals specifically, and I'm definitely not going to ask you about these segments here. Just the P wave, QRS complex, and T wave and what they represent. So if we put that early picture showing the cardiac conduction pathway together with the EKG trace that we see, we can line up these events here. So starting here, which is basically before the P wave, nothing's happening. And then when the SA node starts to fire and it spreads into the atria, we start the P wave here. Now, the entire P wave is colored in because that's when the electrical changes are starting. That's going to spread through all of the atria from the P wave into the QRS complex, which is what's purple right here. Okay, and then that's going to spread down the atrial septum, the ventricular septum along the AV bundle and the bundle branches to the apex, and then start spreading up left and right. And that's when we see the QRS complex. And then as it spreads through everything, as the ventricles are depolarizing, we see the sort of flat line in between QRS and T. And then as it's spread all the way through the ventricles, and the ventricles are starting to repolarize again, that's when we see the T wave. Now, earlier I was saying, maybe this purple should be about halfway up and this purple should be all the way up. Now that I see, looking at this, it's really most sources that have a similar picture to this won't have any purple in the sixth picture because purple represents depolarization and the T wave is repolarization. So there shouldn't be anything going on right here, okay? But that's not quite the way that they laid it out here. And I understand, seeing other books, why they did this. Repolarization of the ventricles and the complete inactivity of the entire heart, as we see here. If we don't color what's happening in the ventricles, these two pictures would actually look the same. So they instead decided to make these two pictures look the same. Whatever. But that's the progression of what's happening as we run through this. Now, back in Blackboard, I have a link here that goes to the Nobel Prize electrocardiogram website. And you're familiar with the Nobel Prize website because we used it for the blood last time. This goes to first a landing page that when I originally put the link in there, the landing page looked better, but for whatever reason, the page doesn't code properly, so you don't see things. But there's white on white text down here. Okay? If you highlight the text, you'll see it. Okay, but also if you just put the mouse in here, it'll highlight the link. The word reading is an inactive link, but it's white on white. So click on this link and it'll take you to an article, very much like the article that we saw for the blood. And it just sort of goes through and talks about all the stuff that I just explained. One thing that I was hoping for, or one thing that's always worked in the past, and I don't know why it's not working now, right here where it says you need Flash Player 6 to play this game, actually what should be there is not a game, but an animation. And I have definitely uploaded or installed the most recent Flash Player program on this computer, and I still get this error message. And I get it in Chrome and I get it in Firefox, so I don't know what's going on there. But for whatever reason, we don't see that animation. We will see something similar to that a little later on, but it's kind of unfortunate we don't see it there. It's just an animation of the conduction pathway, okay? And we'll see that a little bit later on. So it talks about cells being electrically active, and then sort of the big part in here is it's talking about why this is important, why it was the subject of a Nobel Prize. So this guy discovered a way to put these electrodes on the skin and get electrical information about what's going on in the heart. And so let me just go back to, this picture here. So this is the electrode placement that I mentioned a second ago. Just thinking about the right arm, and left leg electrodes. So now we have the arms spread wide. But that basically defines three sides of a triangle. So right arm to left arm is one side, right arm to left leg is another side, and left arm to left leg is another side. That's a triangle. And that's what's called Einthoven's triangle. Einthoven's the guy that got the prize here. If we were to draw this triangle a slightly different way, I missed it. There we go. So we went from the right arm to the left arm to the left leg to the right arm. We drew the triangle on top of the rib cage right here. It would surround the heart, okay? And that's the point here, is this triangle basically outlines the heart. The three lines, which we see in the article here, represent the comparison of one electrode to another electrode. Okay, so right arm to left arm electrode, right arm to left leg electrode, left arm to left leg electrode. Those comparisons of two electrodes give us what we call a lead. And there are three standard leads, which are the three walls of the triangle. Standard lead 2, right arm to left leg, basically is parallel to the axis of the heart, okay? Which, again, if we go here, missed it again. So we have lead 2 going across the chest in this direction, basically. It's parallel to the axis of the heart. When we talk about the shape of the EKG, the pictures I showed you a little bit ago, not there, there. This is, in fact, the recording we get for standard lead 2. We can get a recording from any of the other leads, and there's going to be P waves, QRS complexes, and T waves for all of them. But the shape of those is going to be different because of where exactly we're looking at the electrical activity. So when we see this, it's really the recording we make in this direction. And it's sort of the standard picture that we're used to. It's called standard lead 2. Now, a common setup for an electrocardiogram is called a 12-lead electrocardiogram. There are 10 electrodes, but by comparing at least 2 electrodes together, we can get 12 different combinations. Now, we could get a whole bunch more combinations, but 3 of those leads are represented here, the 3 walls of the triangle. 3 more leads use all 3 points of the triangle, but compare them in different ways. We call those augmented leads. I don't know anything about augmented leads. And then the other 6 leads are based on the chest electrodes. They're called precordial leads. And it's really comparing what's happening at that electrode to at least the grounding electrode and subtracting out all the background noise, if not just comparing it separate from everything else. So we get 6 more leads across there. Now I mention that because when we look at the EKG in a little bit, the leads are going to show up. Okay. But it's based on the placement of those 10 electrodes. Then here they just mention mountains and valleys, which is the waves that we just talked about, P, Q, R, S, T, which just repeats over and over again. And again, this shape is what we would expect to see in a normal standard lead 2 recording. Now, the power of the EKG as a tool is that we can see electrical problems in the heart, and it'll point to functional problems with the heart, and we can make some very powerful guesses about what's going on. So these 2 pictures show kind of a cartoon version of the heart, which is what we're going to see elsewhere. That place where I said there'd be an animation that didn't show up for whatever reason, it would be one of these hearts, and we'd see the SA node flash yellow, and then a yellow line going down to the AV node, and then that travels through the AV bundle into the bundle branches, and then up either side of the ventricles. As the SA node turns yellow, all of the atrial walls will then flash a darker color to represent depolarization there. I guess you could call that purple. And then as the signal travels down the interventricular septum and up the right or left side of the heart, we'd see little segments lighting up representing the spreading depolarization following that part of the pathway. Now, in these 2 hearts, we can see a big black patch right here in the left ventricular wall, which is labeled dead tissue because this is a heart that suffered a heart attack or a cardiac infarction. And so that tissue stopped getting blood because a blood vessel was blocked. And when blood's not arriving, oxygen's not arriving, and the tissue stops being able to make ATP. And the tissue will die as it runs out of energy. Okay. About 10 minutes or so, probably, you start to see dead tissue showing up. But since that's part of the ventricular wall, the cardiac conduction pathway fibers going through that dead tissue are also dead. And so the conduction can't go further through that. Over here, we have something similar. The black patch is here in the top of the left bundle branch. And this is what we call a left bundle branch block. It might be dead tissue, or it might be some other defect of the conduction pathway cells. But the signal can't go down the left bundle branch, and it doesn't go up the left side. Okay. The right side's fine. There's nothing blocking that, but the left side's thrown off. Neither of these is going to make it impossible for the heart to beat, but it's going to act very differently. And because of what we're seeing messed up in the conduction pathway, we'll see evidence of that in the EKG, and it'll help us diagnose a little bit what's going on. Okay.
They can actually both look extremely similar to each other.
Well, the source material we're going to look at is actually meant to look kind of different, so you can see it apart. But yeah, depending on exactly where the infarction lies, it could very much look like a left bundle branch. But the people who are making this are trying to distinguish them better than that. Now, if you continue down here, it says a few other things about stuff that you're already familiar with. It mentions artificial pacemakers, and then it has a link to the electrocardiogram game. Now, just like there was a blood typing game last week, there's an electrocardiogram game. It's a slightly different game, and And oh, that link just comes back to this page here. This is the page that the link in Blackboard took us to. So if you want to look at the article, you can find that white on white text link down here. But really you want to hit this link, which is visible, that goes to play the EKG game. Oh, a word for a second about EKG. Obviously here they say ECG, and I say EKG. There's two reasons I do that. Maybe we should call it three reasons. One, I'm old and I can do what I want. And actually that's more than just a joke. That's actually the reason why a lot of things have multiple names. Old anatomists refuse to change what they say. But that's not really why I do it. I do it more because I get a lot of these done. I have my own cardiac issues, and so I get EKGs done a lot. And switching to calling it ECGs is a fairly recent change. So in my life, most of the time they've been called EKGs, and I always do that. But the main reason I do it is actually for you. ECG sounds very similar to EEG. It's very hard to tell those apart when they're said quickly. EKG is very obviously not EEG. Now, we're not going to study EEGs, but when you're talking about these procedures, you want to be clear about what you're talking about. And so it's best to have a very obvious difference between them. And so I call that an EKG. The K comes from the fact that in German, electrocardiogram is spelled with a K. And Eindhoven, who developed all this, a Dutch guy, back in the, whenever it was, 30s, physiologists were basically Germanic scientists. Physiology was largely based in Northern Europe. And so the de facto language for physiologists was German. Nowadays, the de facto language for pretty much all of science is English, thanks to America's refusal to learn other languages, basically. And so now electrocardiogram is always referred to based on the English spelling, and cardio, of course, has a C in it. So people are tending to use ECG instead of EKG. I will continue to use EKG, mostly because it makes it very clear to students what I'm talking about. So in this game, we have 4 patients that are each named by different colors. You pick one of those patients and hit the intercom button, and he shows up in your office. We know it's Mr. Yellow because he has a yellow tie. So it gives you a little bit of information about him, and then down below represents the dialogue that you're going to have with him. So he says, I was sent here to get an EKG. Is it going to hurt? And so to see your response, hit the little arrow key to the side, and you, in your best bedside manner, say, no, it's not going to hurt. Take off all your clothes and go lay down. Now, I want to warn you, this is made by Europeans, so their sensibilities are a little different from Americans, and so he's wearing yellow Speedos. Okay. But again, it's Mr. Yellow, Mr. Speedo. Mr. Yellow, so yellow color there. And one of the other guys has boxers on, so that might make you feel a little better or whatever. These are the 10 electrodes that we need to place. And so we just drag these onto their location. You hold the mouse over the electrode and it tells you where it goes. So this is the left arm electrode. This is the left ankle electrode. This is the right arm electrode. This is the right ankle electrode, which is the grounding electrode. And then these 6 are all chest electrodes. You don't have to get their placement perfect. Just drag it over to the chest somewhere, and it'll put it where it's supposed to be in the proper order, like that. Once you've done one patient, the next patient, there will be an extra button, I think it's down here, that says, lets you just automatically place the electrodes if you don't want to do that each time. Once you have the electrodes placed, then the arrow key will take you to the recording. Now this is going by in real time, and we'll stop it and slow it down a little bit. But what we're seeing here is the animation. So the animation that wasn't working on the article page was very much like this, except that it didn't have a little black spot right there. So we have the SA node lighting up, and that spreads down to the AV node and then the AV bundle, and it goes down the bundle branches. Of course, this guy doesn't go down his left bundle branch. And when the SA node fires, the atria flash a darker color. When the signal spreads down, to the ventricles, we see that dark color flashing following that. Okay? And that represents the depolarization. Now, what's going on over here is probably going by too fast to really make sense of. But here we have the 1, 2, and 3 standard leads. We can switch to 1, 2, and 3 augmented leads, and we can switch between the 6 different precordial leads, or the chest electrode-based leads. Now, they all look very different. They all have events, which are basically P waves, QRS complexes, and T waves. QRS complexes always stand out. They're going to be the big things, like those, or these things up here, or these things in those leads. But don't worry about that. We're really just thinking about the standard lead number 2. And this is going by too fast to really make sense of, so we can switch from real time to schematic. And now we have some arrow buttons that we can control how things happen. So you hit the arrow button once, and we see the P wave. And that corresponds to the SA node firing and depolarization spreading throughout the atrial walls. Okay? And then it's going to get down to 0 because this lasts for about 100 milliseconds before we start to see any other change. And while that's happening, as far as the conduction pathway is concerned, the AV node is lighting up and it's spreading through the AV bundle. We don't see any electrical change based on this because it's a very small population of cells, and there's just not enough activity in the EKG to register here, because the atria are depolarizing and they're contracting and all that. So the EKG is sort of in its flatline mode because nothing's changing. And then we start to see the QRS complex start off as the signal spreads down into the AV bundle branches. Now, again, this guy has a blockage on the left side, so we don't see it continuing down there, but we can see the right bundle branch just fine. But because of what's happening on the left side of his heart, the QRS complex is not going to look like we'd expect. Okay, so we move on. It keeps building up. We're down to the apex, and it's starting to spread up into the right ventricular wall. There's nothing on the left side because the left bundle branch doesn't allow anything to travel through there. And we're not all the way up the right wall here. Okay? So we're just early in the QRS complex. Then when we get to the peak, we've spread up into the rest of the right ventricular wall. And now we see the entire left side depolarized at once. The bundle branch is blocked, so the signal's not coming through the pathway it's supposed to. What's happening on the left side is it's getting its signal from the right side. As the signal spreads up the right wall, it's going to spread across the right ventricle, and it's going to continue on into the left ventricle. So the left ventricle is getting its signal kind of indirectly from the right side instead of directly from the left bundle branch. Okay. The QRS complex kind of falls off slowly here as the ventricular walls finish depolarizing. Now they're depolarized. We just don't see anything in the animation, but they're sitting at their depolarized state, and the trace has gotten back to its 0 level, and it's going to have a little flat line for a while before it hits its T wave. But the QRS complex slowly falls off. This little bump here is because the left side is depolarizing late and all at once. And then the animation's done doing anything. So when we hit the next button, it just plays out the rest and goes into the T wave. Nothing really happens in the animation. If you want to follow this, you can back up all you want and go forward and see the different things happening. But we can look at the animation here. We see a little black spot in the left bundle branch, and the conduction stops at that blockage. So this is a left bundle branch blockage, obviously. And it corresponds to the picture that we saw in the article a little bit ago. When you hit the arrow button again, you move out of the recording and you go back to your office, and you can look at your patient's EKG. So we have 6 leads up here, alternating augmented to standard, augmented, standard, augmented, standard. Standard lead 2 is the one that we're interested in, that we just stepped through. And then the precordial leads are down here. Over here we have a reference book that has 4 bookmarks in it. And remember, we have 4 patients. So basically what we're doing is we're matching each condition with the patient. So the last one that I'm on here, cardiac infarction, there's a normal example, there's arrhythmia, and then there's blockage. So we're going to match those up with the 4 different patients. Now we know our patient has a blockage. We just saw it in the animation. So we can open up the book there. There's 2 pages here, so there's 2 example traces to match. So it's set up the same way, alternating augmented to standard leads, and then all the precordial leads down here. What you want to do is to compare what you see in the reference to what you see in the patient. There's 2 things you need to do here. One, look at standard lead 2, okay? What we're expecting to see. And for this one, this is a pretty accurate, not accurate, but pretty normal standard lead 2. Okay? P wave, QRS complex, D wave. And the QRS complex, which is the big thing in our guy here, is pretty tight. Okay? Doesn't look anything like this guy. The other thing you want to do is to just generally look at the 2 pages side by side and just see if they look at all similar. And these don't. Okay? If we go to the reference 2 page, which you can do by clicking the little button here, now we have a reference page that looks a lot more like our guy. The standard lead 2 trace here, the reference one has a nice broad QRS complex like our guy. It slowly falls off, again, because of what's happening on the left side of his heart. And then just generally looking at the 2 together, the traces are not exactly the same size, but a lot of the waves that we see go in similar directions. So yeah, they're bigger here than down here, but they're all going down there. More importantly, if we look at all the precordial leads, 1 through 4 in both of these have these big QRS complexes that point downward. They get progressively smaller, but they overlap. And then 5 and 6 are smaller and they point upward. 5 and 6 are smaller and they point upward. So qualitatively, these 2 look pretty similar. The standard lead 2 really sells it, but overall, you can see some similarities there. We know this guy has blockage, and we know this is not right. Reference 1 is not right. So reference 2 has to be right, because we know that that's the problem. So use what you can learn from the recording and the animations to help you pick out the correct references that you want to go with. Once you've decided on which condition the patient has, click here to select it. This guy has a bundle branch block. We know actually it's a left bundle branch block, but this is the only choice we have that fits. And hit OK. And then, so our guy's things disappeared. You can close the book if you want to also, but you don't need to. Hit the arrow to go on, and you have the choice of either calling one of the other patients, which will take you back to the list of patient names and the intercom button, or you can quit the game and see your results. So we only did 1 patient, but Mr. Yellow we diagnosed with a blockage, and we get a green check mark, which means that we're correct. If you get it wrong, you'll have a red X there. If you would like to, you can print out your results. You can hang them up on your refrigerator. You can hang them up on your virtual refrigerator on Flashboard, Facebook, whatever you want to do. I don't care. I'm not looking for your results. You don't have to share those with me. Instead, you have a question based on the results of that game in the lab quiz for this week, just like you had one based on the blood lab quiz last week. Okay. Now, I have a link here that says EKG examples. If you click on this, you get a box page that says there's nothing there. And the reason for that is that I actually took down that page from box because I don't need these examples anymore. Okay, so I'm just going to completely delete that link. It's gone. It's no longer there. The reason we don't need it anymore is because in this part of the chapter, the cardiac muscle and electric activity, after it talks about the EKG, there we go. So the stuff we looked at. Then it has this everyday connection, and it has some examples of abnormal EKGs. And the thing that I no longer had in that link was basically something fairly similar to this. Now, we've seen the normal EKG, which we would call a sinus rhythm. When the sinoatrial node is working properly and everything works correctly, we call that sinus rhythm. These abnormalities show us a few variations when things are going wrong. This is called second degree or a partial blockage. Okay? And what we see here is a P wave with nothing after it. Then we see another P wave, QRS complex, T wave, P wave, QRS, T, P, QRS, T. Wait, what am I missing here? Oh, okay. The example I used to have, it was showing up elsewhere, but there's only one example of it here. So we have P, QRS, T, P, nothing, P, QRS, T. So this first P wave that we see here, which actually we don't actually know that's a P wave, could be a T wave from the previous heartbeat, but let's call it a P wave, just so we have two here. And this P wave right here, don't cause a QRS complex to follow them. Okay. There's something blocking the transmission from the SA node to the AV node, but not all the time. We have several P waves that work here. Okay. This is a second degree or partial block, so that there's something interfering with the signal moving on. Okay. And that problem is somewhere in the atrial wall. So the connection from the SA node to the AV node is thrown off. The next one here is atrial fibrillation. And what fibrillation means is basically sporadic chaotic activity in the muscle wall. Atrial fibrillation is when that's in the atrial wall. And so basically what we see are P wave kind of activity all over the place. Okay. And that's because there's like multiple SA nodes. A bunch of different locations in the atrial wall all become SA nodes. They all become autorhythmic. And so they're sending off their signals, which spread everywhere and cause the atrial walls to just completely go bat crazy. You know the word that comes between those two. And every so often, one of those causes the AV node to send a signal down the AV bundle, and the bundle branches, which is the QRS complex. The QRS complexes are very irregular here because they're not getting reliable signals. Okay. And that's what we see in atrial fibrillation. This is ventricular tachycardia. And I love that this is in the book because it wasn't in the examples that I had before, but it's a good example of something going on. So we have a fairly normal little heartbeat here at the beginning, and then something happens, and the QRS complex kind of takes over. And this will make the heart feel like it's kind of racing. The rate that these contractions are taking place might be a little fast, but they're really big changes, and so it can really feel like pretty serious palpitations that are occurring. Really, you can feel really forceful heartbeats there. Now, when this happens, it usually suggests that there's a problem with the ventricles, which is, in fact, diagnostic of or indicative of what could lead to heart attacks. So when somebody has ventricular tachycardia like this, they're pretty much always going to get a pacemaker put in. And that pacemaker, sorry, not a pacemaker, but a combination pacemaker defibrillator. And what that will do is it will shock the heart or override the activity here and get it back to a normal rhythm. Okay. And that'll hopefully prevent the possibility of a heart attack, which is essentially what we see down below. This is ventricular fibrillation, which, just like atrial fibrillation, just chaotic activity, but this is chaotic activity in the ventricles, which is what would happen during a heart attack. Okay. And then down below, we have here yet another type of heart block. This is third degree block. What's important here is the P waves that are showing up here and there do not correspond at all to the QRS complexes. SA node is active technically in this picture, but it's not doing anything. The QRS complexes are firing off because the AV node can take over when the SA node isn't working properly. The problem is that the QRS complexes that we see here now are spaced quite far apart, saying that we've got a fairly slow heart rate. Earlier, I talked about, didn't quite make it, this activity, and I was talking about what's happening in the SA node. In fact, the SA node does what I described with that previous picture I just showed you. The AV node can do that also, but it does it at a slower rate. The SA node does it at about 100 beats per minute, which gets slowed down by the parasympathetic system. The AV node, if it's not getting a signal from the SA node, will be active on its own at about 40 to 50 beats per minute, which is enough to move blood around your body, get oxygen to your brain and to your important skeletal muscles like the diaphragm, but not enough to really sustain activity. So somebody who's, where'd we go there? Nope. Got this kind of blockage going on where the rhythm is really driven by the AV node. They're not going to sustain activity for very long. They're going to get tired very quickly. And probably there are a number of people out in the world that are like that. And they're just saying, well, you know, I'm out of shape, so I'm tired. I'm just going to sit on the couch and watch television. But really what's wrong is this part of the heart is not communicating with this part of the heart. Could very well be that this part of the heart is not functioning at all, and this part of the heart is driving everything. It's enough to get by, but really not enough to live a normal life. And so there's something that should be seen there. That's often referred to as junctional rhythm because the AV node is at the junction between the atrium and the ventricles, and it's basically setting the pace. Now, if the SA node fails, the AV node can pick up the slack and keep things going, kind of. If the AV node fails and the SA node's failed also, then the ventricular fibers in the rest of the pathway are autorhythmic on their own also. But they're autorhythmic at a very low rate, about 20 beats per minute. 20 beats per minute is not really enough to move oxygen around your body effectively. If you're standing up, it's not really enough to generate the pressure to get blood up to your brain. So you better be laying down if your SA node and your AV node are both checked out and you're relying on that. Also, you should be laying down in the back of an ambulance or in a hospital because you're in a really bad way. But there is a backup plan, and there's a backup plan to the backup plan. But once that fails, you're dead. So there's nothing you can do about it. But hopefully in that series of failures, interventions can take place and something can be done. If the SA node is completely shot and the AV node can't sustain things, then an artificial pacemaker might be put in to drive everything here or something like that. So, whoops. So those are some examples of irregular EKG readings and some blurbs here explaining what's going on with them. And then this goes on to talk about automated defibrillators. You've probably seen medical dramas where somebody says clear, and they shock somebody back from being dead. This is the same kind of thing. This is automatic. You just put them on somebody's chest, and a computer reads their heart rhythm, decides whether it can be shocked and when to shock it, that kind of thing. So it just mentions that there. I was looking at this. I didn't ever really look at this a little bit too closely, but I thought it was kind of funny. Down here at the end in the parentheses, it says, seek additional comment for more detail about metabolism. I think what it is that the author wrote this little bit and put that note in there to themselves so that they'd remember to add to this part, and the author and the editor both forgot to go back and do that. So whatever. But basically all this is saying is that cardiac muscle is pretty much all aerobic. Okay, so oxidative fibers, and that's kind of what it's getting at there. But it doesn't have a whole lot of detail, so the author apparently was saying, I need to add some more detail there. I'll get back to that someday. Never did. So I just thought that was kind of funny. So from here, come on, back to the top. The next part is about the cardiac cycle, which is what happens in a heartbeat. And then some descriptions of cardiac physiology. I want to talk a little bit about this stuff, but I certainly can't do it in 10 minutes. So I'm not going to do that tonight. I don't really talk about development of the heart. If you're interested in that, feel free to look at it. But outside of the learning pod assignments, I don't really have any questions about that in your assignments. But I do want to spend a little bit of time talking about this. So I'll do that in the first 20, 30 minutes of class next week, just to make sure you get this. But of course, you'll be working on this these assignments over the coming week. So please spend some time reading this stuff and working on the assignments. You might want to not submit the Part 4 assignment by the due date, because you might want to listen to what I have to say about that stuff next week just to finish things out for that. But the Part 1, 2, and 3 assignments, since you can go back and do them over and over again, if you go ahead and do them on time and you're missing some of the questions because you didn't quite understand this, you'll have a chance to go back and do them again. So, and also we'll look at the blood vessels next week. Also next week, or actually come to think of it, we got a little bit of time here. So let me talk about this now. I was going to say next week, because we don't have a whole lot to do, we'll finish a little early if things go well, but also it would give me time to talk about the practical. What I actually want to do, since we have a few minutes, I want to talk about the practical briefly. I would probably go on for like 15 or 20 minutes talking about the practical, so this at least forces me to keep it shorter. So next week we're doing the blood vessels, which is going to be the 3rd, and then the week after that's the 10th, and we'll be doing the practical that week. And so I just want to show you what you want to do to start preparing for the practical and what to expect. So if you go back into the weekly material, so here we are with the heart, and next week's the vessels. The week after that is the practical. In this folder, you'll only see 3 things, which will look like this. There's an outline, which is basically an overview of everything that we will have done for the first half of the semester, meaning going through all of the cardiovascular system. And then there's this document that says cases. We looked at that already when we were talking about the autonomic case study that's in there. There's 3 more cases in there. One is about a woman with diabetes, one is about a guy with chest pains, and one is about a guy who went to South America and didn't do the proper procedures before traveling abroad, and he came back with some extra friends. So basically there, we've got the autonomic case study, we've got an endocrine case study, we've got 2 cardiovascular case studies, which covers basically everything we're doing this half of the semester. The cases are there because it's sort of the framework that I build the test. What I do is a little bit different than what you might have had in A&P 1 if you had somebody else besides me. Obviously, if you had me, the practical is exactly the same. But instead of setting things up in this room and you come in and you look at all these different stations and you walk around and that kind of thing, instead, I'm going to give you a more regular kind of test, staple pieces of paper, and you're going to do most of that just sitting at your desk like your average kind of test. The test is based on these cases. It's a 50 multiple choice question test. There are 4 cases and 50 questions. 4 does not go into 50 evenly. So 12 or 13 questions per case. When you come in and you sit down, I'll hand out the test, staple pieces of paper. On the test, right after where you put your name, it'll have the text of case 1, the autonomic case we talked about, right there on the text. You don't have to memorize the case, it's there in front of you, but you do need to study the case ahead of time. And then it'll have the 12 or 13 questions about that case, and then it'll have the text from case 2. And then it's 12 or 13 questions. And then the case 3 and its questions, and 4 and its questions. Those questions, again, they're all multiple choice questions, fall into 3 general types, as I like to describe it. The first type is what I call questions about the case. What I mean by that is I expect that you will look at all these cases and make sure you understand the terminology, you can pull out the symptoms or signs, and link those to the systems that are responsible for it, which is basically what we do with that autonomic case. So I modeled that behavior for one of them, actually the toughest of the 4 cases. And you can just go in and do the same thing for the other 3 cases,
in preparation for the test. So you have questions based on that. It might be questions directly about what's in the case. It might be questions about the basic anatomy and physiology behind what the case is about that we've studied or something like that. The second type is what I call questions not about the case, which might sound a little bit too broad. But the idea here is the cases are very specifically about one part of the autonomic system or the endocrine system or the cardiovascular system. And I want some latitude to ask questions about other stuff. The best way to explain this is in terms of the endocrine system case. So that's about diabetes. Which gland does that mean it's found? Pancreas, right? So if I'm going to ask you questions about the case, that's kind of limiting me to only asking you questions about the pancreas. But I want to ask you questions about other things too. So I have some questions that are not about the case, but still about the endocrine system. So they're responsible for knowing about all the material that we've gone over. So I want the latitude to ask questions outside the context of the case. And then the third type is what I consider the more traditional sort of practical questions, where you are actually looking at some of the material from class. So it might be models like this guy up here, might be microscope slides, might be bones or other specimens, probably not because it's the same V2, but you know the deal. I'll have pieces of tape on the models or the microscope will be pointing at something on the slide. You look at whatever it is and you'll have questions about that specifically. On the test that I give you, there will be a few questions that'll say station 1, station 2, whatever. There will be 8 stations set up, 2 for each case. And you'll come over here and look at something like this model, and I'll have a piece of tape on the model and a question that says something about that piece of tape. Or there will be 4 pieces of tape labeled A, B, C, D, and there'll be a question. Your answer is based on which of those locations answers the questions correctly. So I might ask you, I might have a piece of tape here, A here, B there, C there, and D there, and I might ask you, which is the location of the heart? What would be the correct answer? D. You'll not get that question, that's a little ridiculous, but that's the answer. Or it might be something on a microscope slide, and I'll ask you what the arrow is pointing to, what type of cell, what part of the cell, what part of the tissue. I might ask you about what tissue you're looking at, what its function is, where it's located, that sort of thing. I try to make those questions relevant to the case, but I might have something I want to ask with a model or a specimen that's not directly about the case. So in the dozen or so questions that you have, between the questions about the case and the traditional practical questions that I try to make about the case, probably 8 to 10 of the dozen or so questions are going to be about the case. And 2 to 4 are going to be beyond what the case is about, asking about other things. With the cases, what you want to do is understand what the case is focusing on and know that stuff better. And then the outline sort of shows you what else you're responsible for, and you need to study that. But realistically, you don't have time to study everything. I know that. Fact of life. You're a night student. You probably have a day job. You probably have family. Whatever. So there are things that are going to come up. To prioritize your study and concentrate on what the cases are about. For example, with the endocrine case, concentrate on the pancreas. Know the pancreas well. Recognize it through the microscope, understand the parts of it, understand the physiology of it, how it helps regulate blood sugar levels, that kind of thing. Know that stuff whole. You're definitely going to get questions about that. Then, if you can, study the other stuff. Usually, I think students tend to be able to study effectively probably about 20% of the material in the class. So we're talking about the endocrine system, we're talking about 10 glands. So you're probably going to be able to study 2 glands in detail, maybe 3. So definitely make sure one of those is the pancreas, and then go on to look at other stuff. Now, the other stuff that you should look at is going to be the other stuff that I highlighted in the class. Remember, yeah, sure, there's 10 glands, but we looked at the pancreas, definitely. We looked at the pituitary, we looked at the thyroid and parathyroids, and we looked at the adrenals. Okay? So as you're moving out from the pancreas to start studying other things, be sure you study those more than the pineal gland or the gonads or something like that. I didn't stress those other glands, not likely to ask you questions about those. But you might not be able to study all of those glands that we talked about, the 5 that we saw microscope images of. So if you can't study all of them, be sure you definitely study the pancreas before anything else. And then with the other cases, concentrate on what the case is about, and then move out from that. Now, those other cases, it's a little less easy to say, 10 glands, study this one, that sort of thing. But concentrate on the case, be sure you understand that stuff best, and then move out into the other material. With that strategy, you're going to be able to answer the most questions possible. If you know everything, of course, you should be able to answer all the questions. But it's not necessarily realistic to know everything. Oftentimes, when you're sitting down to take a test, it's pretty much just gambling. Did I study the right things that he's going to ask questions about? I'm telling you what I'm most likely going to ask questions about. So study that stuff first, and it'll make it a little bit easier for you to take the test. I'm telling you this today partly because I had time to kind of run through all of this, but also that will give you an extra week to kind of think about things. So go to that cases document. You should be very familiar with the first case, but you can start looking at the other cases and studying that stuff over the next 2 weeks before you get to stuff. Now, the 2 cardiovascular cases, one's about the heart, one's about the blood. I did that on purpose instead of having one specifically about the blood vessels, because the blood vessels is the last topic, and I didn't want to give you, a big topic that there was a case on right at the last minute. You can't always do that, but it worked out for this particular practical. But that's not to say that I won't ask you things about the blood vessels, because the heart pumps into blood vessels. So across those 2 cases, blood vessels will play a part in what's going on there. But like for the heart, be sure that you understand the blood vessels that we talked about tonight that are connected to the heart more than the other things. And there will be some blood vessels that I'll stress a little bit more than others when we're talking about things next week. You'll know what to pay more attention to if you have the time. So that's what you're doing in class 2 weeks from tonight on the 10th. It's all we're doing that night. We're not going to take that test and then for the other half of the night continue on. The test is designed to be completed in about an hour. You will have up to an hour and 50 minutes to do that, which is the standard length of a day lab. And so that's just the time frame that I always allow. You're probably going to be done, again, within about an hour, but if you need it, you can stay on till, what would that be, 7:20. And then I'll kick everybody out. You'll definitely be done by that time. You might be done earlier, but allow for all of that. And you'll definitely be done earlier than most nights for that night. There's also an online assignment, which is the 3rd thing up there. That's sort of like a bunch of Part 4 assignment type questions, open-ended questions. That's due before our next lab meeting after the practical. Okay, so that means our practical's on the 10th. We don't see each other the next week because that's spring break. And so that's actually going to be due the March 24th, yeah. Thank you. You can go in and look at it now. You can start working on it. Sometimes looking at those questions gives you a little bit of insight on what the case is really getting at. The in-class portion is getting at the terminology, symptoms, and systems thing. These assignments are going to go a little bit deeper and going to ask you to think a little bit more about what's going on in the case, maybe do a little bit more research into the clinical aspects of what's going on in that system, treatments, prognoses, not really diagnoses, because we know all the diagnoses. They're very clear. We told you pure autonomic failure for case 1. Case 2, it tells you she's diabetes. Case 3, it tells you it's congestive heart failure. Case 4 doesn't tell you, but it tells you he forgot to get the treatment to prevent malaria. So you can figure out what's going on there. So you don't really have to worry about diagnoses in this particular one so much, but that's the kind of thing that I might ask a question about there too. Any questions about that? Just very quick run through. If that went by really fast and you want a better run through, I explain this to my AP1 classes in their skeleton lab stuff. So if you go into the recordings on YouTube there and you see the skeleton lab recording, the beginning of that is where I'm explaining it in a little bit more detail to them. If you want to listen to that rather than the 15-minute little blurb that I did here. But, if you don't have any questions, that's it for me.